Hey there, awesome physics students. I wanted to do another example of power in circuits. This one is a bit more difficult, and you may have to watch this video a couple of times to fully let everything sink in, okay? So be patient with yourself. The first circuit I want to talk about here, all of these light bulbs here in these examples are all identical light bulbs. And we assume that they are following Ohm's law and that they have a fixed resistance. Now in real life, of course, that's not exactly true, but for our purposes here, we just want to think about the idealized situation. Okay, so in this case, we have a voltage, the A and B are connected in parallel, but B is not turned on. The question is, what happens to the brightness of A if I turn B on in this circuit? Well, because the voltage drop across A is the voltage of the battery, when I close the switch, the voltage drop across A is not changed. And so since the voltage drop across A doesn't change and the resistance of A doesn't change, that means the current that's passing through A doesn't change. And so the power that A dissipates, whether B is open or closed, is the same. And of course, this is the way our house is wired. Our houses are wired in parallel. And when you turn a light on in one room, that doesn't make the light in the other room go dimmer or brighter. It doesn't affect it. And that's on purpose. Of course, we don't want them to, you doing something in one room to affect the other room. That's not always adhered to, but for the most part, it really is that way. For lights, for sure. Now, let's look at this circuit here. Here we have the voltage of the battery. Here we have a light A, and B and C are in parallel with each other, but C is not turned on. So the question is, what happens to A and B in terms of brightness, meaning in terms of power, if I turn C on? So let's go through step by step here. When I turn C on, what happens to the total resistance? Well, you've added a pathway here. Now you might say, well, I've added a resistance, so the resistance should go up. But think about what you've done is you've added a little side road here that the current can pass through, and so that will actually decrease the resistance, right? So the resistance, the total resistance goes down. What does that mean? Why do we care about the total resistance? Because the total resistance for this whole circuit, even, if this branch of resistance goes down, this is in series with A, and so if this resistance decreases, that means the resistance of A plus BC decreases. The total resistance decreases, therefore the current that the battery provides increases, okay? So the total current increases. Why do I want to know that? Well, whenever the current comes out of the battery, the total current is the current through A. So this tells you that the current that passes through A increases. So that suggests right there that power, that A may become more bright if I flip the switch. Well, let's see what happens to the voltage drop before we decide. So if the current through A increases, remember that V equals IR. R stays the same for that individual resistor, that light bulb. So if I increases, that means the voltage drop across A here also increases. Okay, so now we're getting somewhere. If the current through A increases and the voltage drop across A increases, this means that the power dissipated by A increases and A gets brighter, right? Now what happens with B, for example? Of course, it was off, so that one of course gets brighter. What happens with B? Well, the voltage drop across A increases, but the voltage drop across A and B together is the total voltage drop across the battery. So if the voltage drop here increases, that means that the voltage drop across B decreases, right? So let me write this down. VB is VA plus VB, right? And so if VA increases, this means that VB decreases. If the voltage drop across B decreases, Again, V equals IR. The resistance for B did not change. If V for B decreases, that means that the current through B also decreases. Okay, so now if the voltage across B and the current through B decreases, that is the power. This tells me that these two tells me that the power for B decreases and B will become dimmer whenever you turn C on. Of course, this is a suboptimal arrangement for your house. This is why we don't arrange this for your house. But it's a complicated chain of reasoning. Now you might say, well, the current through B shouldn't, if the total current increases, shouldn't the total current through B increase? Well, it's hard to know whether it splits off or what happens with it. You really have to lean on this right here, that the total voltage drop is the sum of A and B. And if A increases, then B must decrease. That's the only way I know how to do this. Without knowing what happens, without this, you don't know what happens with the voltage drop across B. Therefore, you don't know what happens with the current through B, because it's hard to tell if the current increases to such a degree, just by looking at it at least, what happens with the total current and the current through B and yada, yada, yada. This is the only way I know how to reliably get at this. If you try other methods, you may talk yourself into that. It makes sense, but I do not think that they really provide the logical foundation for this. You really need this statement here. All right? Hopefully this helps you understand with current. And again, if you need to watch this over again, please do so. It is a subtle argument and it's a complicated chain of reasoning. All right?